Okay, let's dive into this. For the longest time, the whole idea of looking up into the sky and seeing two suns was strictly the domain of science fiction. But over the last decade or so, astrophysics has seriously caught up with our imaginations. It turns out, our universe is literally teeming with planets orbiting binary stars. So in today's explainer, we're going to unpack the mind-bending reality of circumbinary planets.
Here's our roadmap for today. We'll start with the reality of two suns, then look at surviving the gravitational dance. After that, we'll cover forging a circumbinary world, the hunt for hidden planets, the circumbinary habitable zone, and wrap up with the future of binary exploration. Let's get right into it.
Section 1. The reality of two suns, fiction versus discovery.
Whenever we picture a planet with two suns, we almost universally think of Luke Skywalker staring out at that iconic twin sunset on Tatooine. And as the European Southern Observatory notes, several planets in this exact configuration actually have been discovered in recent years. Most of the ones we've found so far are chilling on orbits that generally align with the flat plane in which their host stars orbit each other.
But that really begs a fascinating question. If we step away from the classic sci-fi trope for a second, what does a circumbinary planet actually look like in reality? Are they always these neat, flat, coplanar solar systems?
Well, the answer is a resounding no, and a massive discovery from April 2025 proved it. Astronomers using ESO's Very Large Telescope spotted a planet designated 2M1510 ABB orbiting its two host brown dwarfs at an astonishing 90-degree angle. It's what we call a polar planet. Its orbit is entirely perpendicular to the orbit of its host stars. It turns out the architecture of these systems can be way stranger than fiction.
Moving on to Chapter 2. Surviving the gravitational dance, all about the orbital mechanics.
So, how do these planets actually survive up there? First, we need to get our terminology straight. Planets in binary systems essentially come in two primary flavors. You have your S-type, or circumstellar planets, which orbit just one of the two stars, while the secondary star acts like this distant gravitational bully perturbing things from afar. Then you have P-type, or circumbinary planets. These are the ones we're focusing on today. Planets that orbit the center of mass of both stars at the same time.
The crucial point to remember here is that orbiting two moving masses is wildly chaotic. It's a classic restricted three-body problem. To survive this, a circumbinary planet absolutely has to respect the Hallman-Wiegert stability limit. This is the critical innermost boundary dictated by the masses and the eccentricity of the binary stars. A planet must stay well outside this limit if it wants to maintain a stable orbit against the time-varying, chaotic gravitational potential generated by its twin suns.
Because trust me, if a planet forms too close or migrates across that Hallman-Wiegert limit, the results are completely cataclysmic. We're talking rapid orbital destabilization. The planet can literally be torn apart by tidal disruption or smashed directly into one of the host stars. Or, and this happens quite a bit, it just gets forcefully ejected completely out of the star system, doomed to wander the interstellar medium as a free-floating rogue planet.
All right, Chapter 3, Forging a Circumbinary World. Let's talk planet formation.
Knowing just how chaotic these environments are, you have to wonder how these worlds even come to be. And this brilliantly illustrates one of the most violent mechanics of planet formation, the bulldozer effect. Observations show a very distinct lack of small, rocky planets on close-in circumbinary orbits. Why? Well, because massive gas giants form way out in the outer reaches of the protoplanetary disk, and as they migrate inward toward the binary stars, they act like a massive gravitational snowplow. They sweep away, destabilize, or just outright destroy any smaller, rocky terrestrial planets that might be trying to form in their path. It's basically a cosmic demolition derby.
But not all circumbinary planets form the exact same way. We essentially see two distinct pathways. Close-in planets typically form via core accretion, gradually building up mass and then migrating inward until they park themselves just outside the central cavity carved by the binary stars. On the flip side, we also see massive, wide-orbit gas giants, hundreds of astronomical units away. These bad boys are thought to form through gravitational instability, which is a really rapid, top-down process where a massive young circumbinary disk fragments into clumps that directly collapse into giant planets.
Just look at the incredible diversity this creates. We have three totally different characters here. You have the famous Kepler-16b, discovered by NASA's Kepler mission, which is your classic Tatooine-like world on a close, coplanar orbit. Then you have B Centauri b, an absolute behemoth at nearly 11 Jupiter masses, orbiting at an incredibly wide 560 AU. And finally, the rebellious 2M1510 ABB, locked in that bizarre perpendicular polar orbit around two tiny brown dwarfs. The sheer variety of these systems is absolutely staggering.
Chapter 4. The Hunt for Hidden Planets. Let's look at the detection methods.
Now, what's really interesting about this is how the binary nature of these systems actively fights against our traditional discovery methods. If you want to use the transit method, watching for a dip in starlight as a planet crosses in front, you usually look for a strict, repeating periodic signal. But circumbinary planets experience what we call roaming conjunctions. Because the two host stars are constantly orbiting each other, their positions change wildly. This means planetary transits happen at highly irregular intervals. The transit durations change, the timing changes, and sometimes, due to orbital precession, the transits just stop completely for years. It completely breaks our standard automated search algorithms. They just don't know what to do with it.
So, to overcome this headache, astronomers have had to get incredibly creative. Enter apsidal precession detection. Instead of waiting around for a planet to block the starlight, scientists look at the eclipsing binary stars themselves. Using long-term data from instruments like TESS and Gaia, they measure how the binary's orbit wobbles or precesses over time. If that wobble can't be explained by standard physics, boom, it points directly to an unseen gravitational perturber, a hidden planet. This brilliant method actually recently yielded 27 new candidate planets without capturing a single transit.
Which brings us to Chapter 5, the Circumbinary Habitable Zone, and the ultimate search for life. When we're calculating where life could survive around a single star, we use a pretty simple static ring, right? The Goldilocks zone. But out here, we have to use a dynamically informed habitable zone. You have to account for the shifting distances, the combined masses, and the overlapping changing spectral energy distributions of two moving stars. What this means in practice is that day-night cycles and seasons are wildly unpredictable, creating an incredibly complex, constantly shifting climate. It's intense.
Because the gravitational perturbations from the twin suns are constantly tweaking the planet's orbit, forcing it into more eccentric paths, the truly safe area, the permanently habitable zone, shrinks drastically. For a planet to survive here, it can't just rely on its orbital distance. Essentially, if you were standing there, you would need immense atmospheric and oceanic climate inertia. It absolutely requires a thick atmosphere and deep oceans capable of buffering the extreme short-term spikes in drops in radiation as the two suns swing around each other.
Finally, Chapter 6, the future of binary exploration. What is next for us? Well, the tools we have coming online are going to absolutely revolutionize this field. We're talking next-generation space missions like Plato and Ariel that will provide unprecedented photometric precision. Meanwhile, high-precision ground-based radial velocity surveys using instruments like SOFI and HARPS are going to be critical. They are going to break the mass separation degeneracies in our data, confirming exactly how massive these candidate planets really are. Plus, tools like the James Webb Space Telescope will soon allow us to peer directly into those thick atmospheres we just talked about, finally giving us a true census of circumbinary architectures.
Which leaves us with this final crazy thought to ponder. We've seen how violent their formation is, how chaotic their orbital mechanics are, and how wildly their climates can swing. But the fact remains, these planets exist, and they are common. So, if a rocky world actually manages to survive the bulldozer effect, navigate the chaotic gravity of two suns, and buffer all that extreme radiation, could someone standing under a twin sunset right now be looking back at us? Thank you so much for joining me for this explainer, and as always, keep your eyes on the stars.